In question 6, we need to sketch the graph of y equals 2 to the power x, where x is a real number, and show the coordinates of the point at which the graph meets the y-axis. You can see in the lower left-hand corner of the screen the function in blue, and it crosses the y-axis at 0, 1, and that's because when x equals 0, 2 to the power 0 equals 1. I haven't sketched the graph when x is negative. In a moment I'll use my Casio graphical calculator to take a look, but I suspect that the x-axis will be an asymptote for this function, because 2 to the power x can never equal 0, although it can be made small by changing the values of x. So if I use my graph function menu, option 5, and key in my function 2 to the power x, and then execute, and F6 to draw. Okay, you can see there that it intersects the y-axis at 0, 1, and we could use gsolve to confirm this. That's F5, and then F4 for y-intercept, and indeed that's 0, 1. And also it does look as if the x-axis will be an asymptote. However, if you look just over here on the left, it looks as if the function is touching the y-axis. That's purely just because of the scale. Now, one way to confirm this is actually to select F5 for gsolve. If I select F1, which I'll do in a moment, for root, it should give me any points of intersection of the function with the x-axis. If I select F1 then, it actually says not found and asks me to press exit. The reason for that is because the curve actually does not ever touch the x-axis, so indeed the x-axis isn't asymptote. If I press exit and draw again, if I change the V window, F3, by altering the values in V window, it may be more obvious that the x-axis is an asymptote. Let's try by changing the y minimum to minus 0.5 and the y maximum to 0.5. When I select execute and one more time and F6 to draw, well, this time you can see that the function doesn't actually touch when x is around minus 4 or indeed minus 5. And just to use more of the function display, I'm going to restrict the values of x. So F3 for V window, and I'll change the x maximum just for now to 0 and see what effect that has. Execute, and again, and F6 to draw. And again I get a clearer representation. Although I can't see the positive part, I can see that the x-axis will be an asymptote. Now in part B, to complete the table, I simply need to key in values. For example, when x is 0, 2 to the power 0 will be 1. When x is 0.6, 2 to the power 0.6 should give you this value to 3 decimal places. That's 1.516. And if you do the same for 2 to the power of 0.8, you will get 1.741 to 3 decimal places. In part C, we need to use the trapezium rule with all the values from my table to find an approximation for the value of the integral of the function between 0 and 1. You can see near the bottom of the screen the value I obtain using the trapezium rule is a total area of 1.4452, and of course this is an approximation. I'm now going to use the Casio graphical calculator to integrate this function. Now the first thing I'm going to do is make sure that my V window settings incorporate the x values from 0 to 1. So I need to change the V window. I can keep the x minimum at minus 5, but I'll change the maximum, let's just say to 2, to make sure it covers x equals 1. And execute twice, and then F6 to draw. Okay, now I wish to integrate the function between 0 and 1, And although I can do it, it's better if I change the V window so that I can see more of the y-axis. So let me change the V window settings for y minimum to, let's say, -2 and the maximum to 10. And F6 to draw. Okay, I now wish to integrate this function. So F5 for gsolve, and I need to use F6 to move to the integration section, which is F3, and I wish to integrate with respect to x, so that's F1, and it's asked me up here, you can see near the top of the window in the calculator, for the lower limit value. Well, that's going to be 0, and execute, and it now asks me for the upper limit value in the top part of the window, and that's when x equals 1, because you can see over here the integral is between 0 and 1. So I select execute, and you can see it gives me a value of 1.44269504. Now remember that our answer was just an approximation using the trapezium rule, so we can just use this as a method to show that we are close to the real value.